Then how does OTV work? So this is an example of a layer 2 traffic between two sites. So we have server 1 in site 1 and server 2 in site 2. So what has happened before this packet can be transported across the core? The server 2 has started communicating in that local network, and this Nexus 7000 device, which is in the site 2 with IPv, it has learned that MAC address. And what it has done, it has advertised that MAC address to the other sites by using the multicast group where all the other sites belong to. So this node here, it has this IPA, learns that, hey, that MAC address 2 is at the other side of the core. And it builds a MAC address routing table based on that information. So when server 1 wants to talk to server 2, that OTV node inside site 1 knows that, hey, we have to transport this across to the other side. And it does that by encapsulating that MAC frame inside IP packet. And the destination address of that IP packet is the address of that OTV node at site 2. That's how it works. So no pseudo wires, only packet-based transport. So I briefly touched the Atlas learning mechanism, how it is done. Here we have more details on that. So in the local site, it works just like before with layer 2 switches. So based on flooding, so when you do not know where to send traffic, send that to all interfaces. Based on that information, the OTV node learns about the local addresses and builds a MAC address table there. And then it will send an OTV update on a multicast group that also contains the other sites, the other OTV nodes. So they will automatically receive an update telling that, hey, these 3 MAC addresses are available in site 1. So if any host at site 2 or 3 wants to communicate with those MACs, those OTV nodes know about this. So this is a built-in mechanism for updating the MACs. Okay, so based on this, it's obvious that we need multicast capability in the IP network. But then there may be instances that, okay, the service provider does not run multicast, so it's only a unicast-based transport network. OTV can run on top of that as well. But then one of these sites has to become a so-called authoritative site. So it is going to act as a hub for the layer 2 traffic to the other side. So that's going to kind of emulate multicast by replicating the traffic to the other side. So for instance, if site A is site 1 is the authoritative site, and site 3 wants to talk to site 2, then the traffic must go first to site 1, and he will then carry the traffic across the site 2. So it is not optimum case when you do not have multicast, but it works as well. Then, how do we handle unknown unicasts? And this is one of the problems with traditional layer 2 networks. When you do not know where the destination is, then you will flood. If you flood across a core network, that's not a very good idea because you're consuming bandwidth really without no reason. So, therefore, OTV does not flood across the core. The assumption is that all active stations that are in those networks, the MAC addresses of those are learned by the OTV nodes and automatically advertised to other sites. So, for instance, if there is a situation where the MAC address is unknown, we still are capable of learning that. For instance, when host here wants to communicate to an IP address and does not know the MAC address of that, then what happens? Sends an ARP request. And the ARP request is intercepted by the OTV node and then carried across to the other sites, and the ARP reply is then intercepted by the local OTV node in the same site where the destination is. And then this address advertisement mechanism will bring the information back to site 1, and then MAC 1 can talk to MAC 3 and register the other side of the network. Multi-homing, that's the other new thing which is built in OTV. It's automatic and works kind of the same way that we have in the first hop redundancy protocols like VR or P. So two nodes will form kind of a virtual pair, but only one of them will be active when it comes to multicast and broadcast traffic forwarding. So as the result, what we will have is automatic built-in loop prevention, because only the primary node will forward multicast and broadcast to the other sides, then it is not duplicated and there is no loop across the core. If the primary node fails, then the secondary node called EAD the secondary node will take the responsibility of the primary node called as ADD. And the spanning tree domain, those will keep localized, so spanning tree is not carried across the core. Although when it comes to broadcast and multicast, we only have one active node in the network. For all other traffic, so meaning unicast traffic, unicast flows, both nodes will still be active. So they will both forward traffic, and when forwarding traffic across the core network, they will use equal cost load balancing. So also at the other side of the network, both nodes will actually forward traffic. So we will have the full bandwidth available for interconnection, not just half of it like we have, for instance, in VPL. But that's a kind of rough overview of how OTV works, what kind of benefit it brings for layer 2 interconnection between data centers. And like I said, it's going to be available for Nexus 7000, which is our layer 3 core platform for data centers. But other platforms will follow during this year. So if you have any questions now, I think I have a couple of minutes to answer. Yeah.
How about the Ethernet multicast?
How about Ethernet multicast? That's the question.
Yeah.
Where the destination address is unknown and formed from the multicast group address?
Could you repeat?
Okay.
Yeah.
So how you were talking about what to do when the destination address is unknown. So what happens with Ethernet multicast addresses?
Ethernet multicast addresses are treated like IP multicast, so those will be flooded to the other side. So the EAD will take care of that. So the unknown unicast was a special case where we do not flood, like we only